Hello. In episode 2, I showed you the usage block at the bottom of every API response. Input underscore tokens, output underscore tokens, cache underscore read underscore input underscore tokens. I told you that's where money lives. Today I'll show you exactly how much each of those numbers costs, why output is always 5 times more expensive than input, and how to calculate the cost of any API request before you even send it. By the end of this episode, you'll never look at an AI bill the same way again. Here we'll understand what is meaning by token. A token is a small text piece that an LLM reads and processes internally, representing each word. An example for story that give a number to its sentences, and for every sentence we show token per word in each sentence. But take care, not only word ranks control number of tokens per word, but also there are other factors that control how many tokens per word will show next scene. Hello, this is the lab part. In this lab, we'll show how token is counting per word. Let's start. First, we import Python library named ticktoken. This is a Python library that converts normal text into tokens that a LLM model can understand. Secondly, we use getEncoding method for library ticktoken. In this line, we're loading tokenizer vocabulary. So here, CL underscore 100K underscore base have a meaning. For CL means represent chat, and 100K is the represent the token vocabulary size. This is a given text example that will show on it how the token is counting. This composed of 4 sentences. Then use encode and send the text. This is just to convert text into a list of token numbers. And this is line for just make a split for the words to make a comparison for each word and the number of tokens. A for loop for every word, just to show the length of for word, and other a for loop to show the length of token. Let's see the output of this code. After I make a run for this code, and this is output. The output here show the full text. Full text already we import, and number of words is 28, and the number of tokens is 33. This result show number of tokens greater than number of words. That means some words convert into 2 tokens or 3 tokens, not only 1 token. And below will show every word and every token length in the given paragraph. For every word, this is a word, and this is token count, and this is ID number. Okay, then this is next word in the line in above paragraph. This count 1 token also. You see, every word here is count as 1 token. But if you go down to check for words that take 2 tokens or 3, we find the word loved. Loved is a word take 2 tokens, L, O, and VED. So this word is counting for our models as 2 tokens. Although this is short size of the word, however, the token is counted into 2. Also, if you go down again to check the number of tokens, we'll find the word morning. These words also count as 2 tokens, for MOR as 1 token, and the NING is second tokens. If you go down again, we find word internationalization. This is long word and counting as a 2 words. And also for the word, it counts as a 2 word, and last one, tokenization. And this is the brief of the word that is count to 2 tokens. So our conclusion here is not only words lengths determine the token lengths, but also there are some factors determining the tokens. This factor will show in the next slide. Not only word length control token per word, but there are many factors affecting in how many token per word. Number 1. Frequency in training data. Tokenizer stores very common patterns as single tokens. Number 2. Common subword patterns for pieces. Number 3. Rare or complex words. That words that rare to use and long length words. Number 4. Spaces before words. Leading spaces may create different tokens. Number 5. Punctuation. Punctuation often becomes separate tokens. Number 6. Capitalization. Uppercase/lowercase may tokenize differently. Number 7. Special characters and numbers are often split. Number 8. Tokenizer vocabulary. Different models use different token rules. Now it is time for most important part in this episode. And this is token cost formula. This is the one formula every AI engineer needs to save in their head. Let us understand and show worked example for token cost calculation. Our example will show for most famous 3 LLM models, Claude, ChatGPT, and Gemini.
Cost formula is calculated per 1 million units and composed of 3 factors. Input equals everything you send. System prompt plus user message plus conversation history plus RAG context plus tool definitions. Output equals everything the model generates back. Cached underscore input underscore token equals repeated input content the provider already processed for you, approximately 10% of input price.
Remember, in episode 2, we learned that input token, output token, and cached input token, you can extract their values from REST API response message. In next section, we'll compare the token pricing of the 3 most widely used LLMs, ChatGPT, Claude, and Gemini, covering input, output, and cached input token costs based on the official prices available during this episode's recording. I pulled these directly from the official Anthropic, OpenAI, and Google pricing pages today. All prices are US dollars per 1 million tokens. For ChatGPT models, GPT 5.3, GPT 5.4, and GPT 5.4 mini. GPT 5.5 currently costs $5 per 1 million input tokens, 50 cents per 1 million cached input tokens, and $30 per 1 million output tokens. GPT 5.4 currently costs $2.50 per 1 million input tokens, 25 cents per 1 million cached input tokens, and $15 per 1 million output tokens. GPT 5.4 mini currently costs 75 cents per 1 million input tokens, 7 cents per 1 million cached input tokens, and $4.5 per 1 million output tokens. This means GPT 5.5 provides the highest capability among these models, but generated responses, output tokens, are significantly more expensive than sending prompts.
GPT 5.4 costs $2.50 per 1 million input tokens, 25 cents per 1 million cached input tokens, and $15 per 1 million output tokens. It offers a balanced trade-off between performance and cost, with output generation still being the most expensive component. GPT 5.4 mini costs $0.75 per 1 million input tokens, $0.07 per 1 million cached input tokens, and $4.50 per 1 million output tokens. This lightweight model is much cheaper for high-volume applications, especially chatbots or automation systems that require lower operational costs. For Claude LLM, Claude Opus 4.7 costs $5 per 1 million input tokens and $25 per 1 million output tokens. It is Anthropic's most powerful model for complex reasoning and agentic coding tasks. But output generation remains significantly more expensive because generating responses requires heavier computation. Claude Sonnet 4.6 costs $3 per 1 million input tokens and $15 per 1 million output tokens. This model provides a strong balance between speed, intelligence, and operational cost, making it suitable for production AI assistants and enterprise workflows. Claude Haiku 4.5 costs $1 per 1 million input tokens and $5 per 1 million output tokens. It is the fastest and most lightweight option among the Claude models, designed for low latency and cost-efficient applications such as chatbots, summarization, and high-volume API workloads. Gemini 3.1 Pro is $2 per $12 per 1 million tokens, under 200,000 prompt tokens. Gemini 3.1 Flashlight is 25 cents per $1.50. Hello. Now we'll show the Python lab for model cost calculation for 3 models: Claude, ChatGPT, and Gemini. First, we'll start to install Panda library, then import Panda. This needed for showing the table comparison at the end of this code. Then I assume some values for the input token and output tokens and the cached input tokens. For input tokens, I assume 100,000. For output tokens, I assume 20,000. And for cached input token, I assume 50,000. Okay. Then define a dictionary. Name is models. This contains all providers, so 3 providers, and for every provider contains the models. For OpenAI provider contain 4 models, and for each model contains the input price per 1 million token, the output price per 1 million token, and the cached price per 1 million token. Followed by the Claude provider for the 3 famous models for the Claude: Opus 4.7 and the Sonnet 4.6, and the Haiku 4.4, 4.5. Followed by Gemini models. Gemini models that define here 4 different models. Then followed by creates the functions named calculate_cost that takes 4 inputs: the input token, the output token, and the cached input token, and the price. And then for every 3 factors, for the total cost, for the input and the output and the cached cost, I calculate the cost by firstly define the input token divided by 1 million, because the unit of the price always used is per million token. Then multiply by price of the input. For the output cost, also divide the output token by 1 million, then multiply by price of the output. And for the cached cost, I divide the cached input tokens by 1 million, then multiply with the price of cache. Then for total cost, I make a summation for the input cost plus output cost plus cached cost. Then return the result of the input cost, output cost, and the cached cost, and also the total cost. This is a function named calculate cost. Okay.
Then I start to build a comparison table by define for loop. This looping over all items of the model's dictionary that I defined above. So here, per every model for the input and output and the cache, I here make a for loop. By define the created function name calculate underscore cost and send 4 inputs and then return the 4 outputs result of the calculation cost. Then make like append for the provider and the model and the input cost. By round the input cost calculated for 6 digits and output cost rounding by 6 digit, and the cached input cost by also round by 6 digit, and the total cost by rounding. Then create data frame for the rows. So the output of the here is the output of the append of this result. Okay. Make this into data frame, then make a sort underscore values by total cost. This make by sort underscore values from the lowest to the highest to check with the lowest model in price and the highest model in price. Okay. If we run this code, we'll show this result. This result is showing 12 models value where the input cost calculator cost and the output calculator cost, and also the cached input cost calculated, and the total cost is the summation of the input and the output and the cached input cost. Okay. From here, you can find the lowest model in the cost is GPT 5.4 nano, and the highest cost model is GPT 5.5 with the cost around $1.12 for our models, and for the lowest one was $4.1325. So from here, I found this token, okay? This defined token, if I use the lowest one, I will pay for the token usage for single request. I will pay around 0.01325, and if I use the largest one for paying for this text per single request, I will pay $1.12. Okay? So the cheapest models from this will be GPT 5.4 nano with this dollar percentage. So now you can estimate the cost of almost any AI request before even sending it by understanding how tokens, model pricing, and caching actually work behind the scenes. But calculating cost is only the first step. In the next episode, we'll move to the most important part, AI cost optimization. We'll explore 4 powerful optimization layers that can dramatically reduce token usage and API expenses in real-world AI systems. We'll cover techniques like output control, conversation compression, RAG optimization, semantic caching, model routing, and batch API processing for up to 50% lower cost. And for every optimization method, we won't just explain the theory, we will also implement real Python code examples step by step. See you in episode 4.